In the easier transformations in the world of stretches and shrinks, this gives us the last vertical transformation, which is a vertical shrink or a vertical stretch. And we saw yesterday a vertical stretch is if I would grab my arms up, it narrows the graph, and if you push down, it widens the graph. So stretches make the y values bigger, shrinks make the y values smaller. When you're dealing with the y values, it is what it is. I mean, it's of a 2, it's a 2. It's a half, it's a half. No matter whether you're multiplying the function or whether you're adding a number or subtracting a number from the function. It is what it is because it's outside the function. So that means when I look at 1/2 x squared, I look at what is the basic function. The basic function is x squared. And x squared's domain is all real numbers. So as a result, that's why I have -2, -1, 0, 1, and 2. And so I'm going to set up my chart. This is 4, 1, 0, 1, 4. Now, by the way these guys work, and when we get into chapter 3, it becomes even more evident. The only thing you would need is 3 points, 3 particular points, to really get a good graph of what you would need. Because if I were to look at the basic, I'm going to pull, here's the squared thing. And then here's this guy right here, our old graph paper here. And I put the basic on top, that if I were to just pull -1, 0, and 1, you would get the bowl on the graph, and then the arms would go out for there. So as long as I had those 3 coordinate points, I basically would have the graph. Because those are the principal points that really give you the shape. The extra points there give you a better shape. So you can do it easily in 3. And by the way, when I ask you to do transformations on your test, I don't ask you to do more than 3 points. It seems to be that 4th point, it just takes forever, for whatever reason, as you'll see. So we're going to go ahead and just do the 5, and that says, what is this? This is a 1/2 sitting in front of x squared, so how would you describe it in words? It's on your table, it's on your chart. What would you call it? Is it a stretch or a shrink? It's a shrink because it's 1/2, right? Makes the y values smaller. And because it's on the y values, it's not horizontal but vertical. So this would be, and I normally just put V shrink, because we're going to have 8 shrinks. And its factor of 1/4. That's your multiplier. Oh, 1/2. I don't know where I got the 1/4 and why my mind was thinking 4. And that tells me to perform this guy, I'm going to take 1/2 and multiply it times the y values. So the only guy who's going to get impacted is y. So that means on my T-bar chart that I've created, I'm going to multiply the y values. That's the only thing I need to do, by 1/2. So this gives me 2, 1/2, 0, 1/2, 2. And then remember, the outside is always my new, because I did nothing with the x's. So if x is -2, y is, by the way, do I expect this graph to be wider or narrower? Wider, right? Because it is pushing down. So the y values are coming down. They're getting smaller. When they get smaller, the graph gets wider. So at -2, it's 2. At -1, it is 1/2. At 0, it's 0. At 1, it's 1/2. At 2, it's 2. Now there's the bowl, and then the graph is going to go up from there. If I wanted a better picture, I would need more coordinate points. Now we expect it to be wider. So this happens to be the graph of f of x equals 1/2 x squared. So that's the graph of. If I want to graph the basic function, it would be -2, +4, -1, +1, 0, 0, 1, whoops, this is a 1, 1, 1, and 2, 4. So, does it meet my expectations? This is the basic graph. Is my new graph wider than my old graph?
Yes.
Yeah, and that's what the vertical stretch does. The last one is the horizontal stretching and shrinking. Now, horizontal stretching and shrinking is of the form, this actually should be absolute value of C, because if C is negative, I've got a flip in there, times X. And you notice it's inside and it multiplies the X values. So examples would be 3x, the quantity squared, the square root of 1/2 times x, the absolute value of 4x, and 3/2 x cubed. Notice that the constant is inside where the x's are, so the operation is on the x value. Now the question is, what does it do to the x value? Poor little things. Okay. Let's see. Well, you were a good parabola yesterday. We'll make you a good parabola today. Parabola. Now, remember we're on the vertical. I'm taking his arms, pulling it up, which makes it narrower, pushing him down, which makes it wider. That's vertical, right? Now, on the horizontal, you're operating on the x values. So that if I do a horizontal stretch, I'm grabbing his arms, stretching them apart. What does it do? It gets wider. And if I'm doing a horizontal shrink, I'm making it narrower. It is the absolute reverse. Thank you. It's the absolute reverse of the vertical. So in other words, if you give me a wider graph and you say, is this a horizontal or a vertical, I can't tell you. If it were wider, it could be a horizontal shrink, but it could be a vertical stretch. They're reversed in appearance. Scary. But think about the x's. The x's are always the reverse of what you think they are. If it's an x plus 2, it's really a minus 2. If it's an x minus 2, it's really a plus 2. So it's the reverse of what you think they are. When you're dealing with the x's, everything is reversed. Which means this. If it is a 3x, it's not really 3x, it's 1/3. And if it's a 1/2 x, it's really not 1/2, it is a 2. Now, this is how I remember it. And how I remember it is, and this is that when I'm dealing with the x's, I look to see if I have 3 times x, that's the transformation, what do I multiply by to bring it back to the original x value? I've got to relate it back to the original. What do I multiply by to bring me back to the original x value? If I had a 1/2 x, what would I multiply by to bring it back to the original x value? 2. So I'm always taking it back to the original x. If you're on the y side, it is what it is. Well, why? Because it's on the outside of everything. But when you're on the inside, everything is reversed. The same thing is true for if I were to look at x plus 3, and maybe it's an x plus 3 squared. I don't know whatever it is. It's the argument of some function. I would look at that and say, what x value do I need to have so that when I add 3 to it, it brings me back to the original origin, the origin of x, which is 0. What would I have to have? -3. The other way to remember it, of course, is always x minus and minus 3. But if I want to think about what brings me back to the original, brings me back to the original is a -3. Brings me back to 0. So when you're dealing with horizontals, horizontals is the reverse of what you think it is. So that when I now look at horizontal stretch, and there should be a shrink in here. There should also be a shrink in here. Horizontal stretch and shrink, this is f of the absolute value of c times x. And to keep things in the same vein as the vertical stretch and shrink, I say it is the reciprocal. So if 1 over the absolute value of c is positive, I have a horizontal stretch. The reciprocal. Remember, if it's a 2, it's a 1/2. If it's a 1/2, it's a 2. So if I take the reciprocal of what this multiplier is, that number is not only what I'm going to multiply the x's by, but that number tells me whether or not it's a stretch or shrink, just like it told me whether it was a stretch or shrink here. And if 1 over the absolute value of c is negative, it is a horizontal, not negative. Oh, Peterson, sometimes I wonder about you. Greater than 1, less than 1. It's a horizontal shrink. And it's going to be performed by taking 1 over the absolute value of c times the x value. So it's going to be just acting exactly like your vertical stretches and shrinks. So if I look at 3x squared, c is 3. So that 1 over the absolute value of 3 is 1/3. And 1/3 is a shrink. And my multiplier is 1/3. If I look at 1/2 x, c is 1/2. 1 over 1/2 is 2. That's a horizontal stretch. And my multiplier is 2. If I look at 4, c is 4. And it's 1/4. My multiplier is 1/4. 1/4 is a shrink. So that brings it into, I don't have to remember that everything is reversed. The number that I get, if the number is smaller than 1, it's a shrink. If the number is bigger than 1, it is a stretch. Whether I'm looking at the reciprocal or whether I'm looking at the number in front of the function. So basically it is of the form f of the absolute value of c times x, and it's performed by taking 1 over the absolute value of c and multiplying it times the x value. This is the hardest of all the transformations because of the reversals. Good news for us, it doesn't have a heck of a lot of meaning.